considered one of the more beautiful objects he has even encountered in mathematics. And they are a sort of quintessence of what is more essential in algebraic geometry. Okay, so it's a strong expression of interest by Grothendieck about these objects. And indeed, we can move to slide number 3. Modern theory of modular spaces started in 1979 with a paper co-authored by Deligne and Mumford, the irreducibility of the space of cursors of given genus, which is in some sense the starting point of the modern theory. Before, also the Italian school of algebraic geometry had ideas and conjectures about modular spaces, but it lacked a rigorous definition of them. A formal construction of modular spaces was not available before this paper here, and so a formal mathematical theory of them was not possible. This paper was the first one to do that, to introduce the notion of stack, algebraic stack, in order to give a precise structure on the modular space of cursor. And since then, the compactification, the standard compactification of the modular space is called the Deligne and Mumford compactification. And that has been widely investigated. In slide number 3, I mentioned one paper I know because it was the starting point of my PhD thesis a quarter of a century ago, a paper by Algebraic about the topology of these modular spaces. And I could put many other references, of course, but at the beginning of slide number 4, I put maybe one of the last, the most recent ones, published on a very good journal, also Mathematics, in 2024, 2 months ago, and essentially in the same spirit, the paper by Algebraic quoted at the end of the previous slide. Okay, so it is a research field which is very active, and still today, this paper published on ANAS is exactly of a few years ago. And so we can go back to Grothendieck, having in mind this paper by Deligne and Mumford, and in another point of Kontsevich, Grothendieck discusses precisely this contribution, this paper, and he observes that Mumford, who was an expert in algebraic geometry and interested in the geometry of modular spaces, had been arrested by technical difficulties about the definition of the structure, the proper structure of the modular space, and the Deligne came into play to help him to manage this situation. And going on with this citation by Grothendieck, we can go to slide number 5, the next one, and shortly later, Grothendieck points out that the idea of the right structure on the modular space is contained not explicitly but implicitly in a paper of him going back to 1971, which is published back in the Senior-Cartan papers. And in slide number, at the end of slide number 5, you find the precise reference. And Grothendieck, in Kontsevich, points out that the language of sites and topos that was not available at the time, beginning of the 60s, but the ideas were already there, and one can read them in his contribution to the Senior-Cartan by Grothendieck himself. So, if we go to the next slide, slide number 6, the comment by Grothendieck is about this operation by Deligne of using the new notion of algebraic stack to introduce the right structure in the moduli space, a sort of misleading operation, because as you can see in the citation, this notion of algebraic stack hides somehow the origin, the root of the idea, the principal ideas contained in the paper by Deligne and Mumford, which of course go back to the theory of topos and site by Grothendieck. And so my question, and that's really the real question, I really would like to listen to your point of view about, if you like, and is to take seriously this remark by Grothendieck. And the natural question, according to me, is if you consider this moduli space and its compactification not as an algebraic stack, as the Deligne and Mumford did, but as a Grothendieck topos, many these different approach have an interesting consequence on our understanding of the geometry of the spaces. Okay, it is a part which was not done by anyone. All papers after Deligne and Mumford use the definition given in the paper, in that paper. So the suggestion by Grothendieck is that it is a poor definition. The right one should be the one in terms of toposes. And so what can be the consequences of these different approaches suggested by Grothendieck? And so I am really curious to hear your comments and suggestions. Before giving the room to your possible comments, I will attempt a partial answer. And my feeling is that if you are interested just to modulate space of curves, and I am going to slide number 7, perhaps the answer is no. So, according to experts in algebraic geometry, the structure of algebraic stack is perfect to define the geometric situation from moduli space of curves. So, taking the introduction of the language of toposes just for that specific moduli space would be not essential. But there are good reasons to think that the range of topos is the right one if one wants to study the geometry of other moduli spaces which are strictly related to the original classical moduli space. And again, I am not sure about what I am saying, but my feeling is that there is a philosophy which was expressed for the first time by Maxime Kontsevich in 1994, which is the philosophy of so-called hidden smoothness. I have a quotation here by Maxime, I can read just a couple of lines. One basic problem is that the moduli space of stable maps, so not of curves, but of images from a curve to a cursor to a fixed target variety, is almost never smooth for higher genus. Maybe this is not a serious obstruction if one adopts the general philosophy of hidden smoothness. To be more precise, we have to wait a few years, and there are a couple of papers by Claudio Fontanari and Capranov, which I quote in the next two slides, slides number 8 and number 9, and I reported a passage from the introduction of the paper by Claudio Fontanari and Capranov devoted to derived Hilbert schemes, is slide number 8. And again, is here in the introduction, they gave a formulation of this hidden smoothness philosophy. Line number 3. In order to avoid the difficulties related to the singular nature of the moduli spaces in geometry, one can pass to the derived category in some sense. And the resulting geometric objects are not ordinate varieties or schemes, but in a different sense, they are expected to be smooth. This is, of course, is once, just once. But if you go to the next slide, slide number 9, you find the little example of mathematics. This is again taken word by word by the figure by Claudio Fontanari and Capranov. You take a smooth projecting variety as a target, consider the stack of maps of fixed genus to the prescribed target with fixed degree, and this is a method. This is an algebraic stack which is non-separated and possibly lossless. There is a natural notion of stability for these objects, and one considers so this natural subset of this locus consisting of maps which satisfy this condition of stability, and if one sticks to this sublocus, we get a proper linear stack separated of finite type, but definitely not smooth. Okay? It is not smooth, and the philosophical reason is that its tangent spaces are obtained by truncating some naturalized objects, such as truncation, which makes the smoothness property to be lost. And so, in this paper, Fontanari and Capranov construct a derived version of the Moduli space, and the theorem whose statement is the last line of slide number 10 is that this new version, this derived version of the moduli space, is indeed smoothed in the algebraic category. As a G stack, it is the differential gradient stack is smooth. So, this is a clear example of this hidden philosophy. Now, what about topos? If you look for the word topos on the side in this paper here, you won't find it. There are no mention of toposes in this paper, but the language is the one of the GeoGebras and statistics. But, and this is my last slide, a few years later, in 2004, there was the PhD thesis by Jacob Loury devoted to a deeper connection of derived algebraic geometry. And as you can see in slide number 10, I have here a couple of notations taken by the thesis of Loury. Here, the natural language is the language of toposes. Even more, the language of infinite topos. So, my feeling, but again, I am not an expert, so I would like to ask you. I think that Grothendieck, even in this stage, and the ability to look further and then far away, to understand that the language of topos theory is essential to put in the right framework the theory of complex spaces in general. Maybe not, it is not essential for the specific case of Mondovì, but as soon as one takes, for instance, a map, cycle, a curve, then that's the right notion, the right language to express the theory of complex spaces. This is my feeling, but I'm very curious of yours. So I would like to finish going back to slide number 6. The open question for me is really open, and I thank you for your passion, for your attention, and I would like to know your point of view, boss. Thank you very much.
Thank you very much, Claudio, for this inspiring and also historically interesting presentation.
Sure.
So, are there any questions or great guys that want to question first of the G-Post? No, please.
Yes, we are going to talk about that.
First, I like Dr. very much because I asked myself the same question. So why did Grothendieck said that the knowledge of toposes would be better to think about moduli problems? And so I want to make some suggestions. So I am not sure, just as you, I am not sure what the answer. The point is that for Grothendieck, the classification problem means introducing a contravariant factor, which may be set-valued, or a group valued, or category valued. So this means it may be a species on some underlying category, which is the category of indexing spaces. So typically the category of schemes. And then when you want to classify some type of structure in the way Grothendieck sees it, of course, it is always, you consider structures in families indexed by base spaces, which typically are schemes, and you also need, of course, payback functors when you classify. Okay, so for Grothendieck, it is a basic classification problem. So typically, at the base, he has the category of schemes or the category of the byte schemes, together with arithmetic topology or rectangle topology or possibly another topology, and is trying to classify some kind of geometric structures which are indexed by the base schemes together with a payback transform. So, for instance, in the lecture by Deligne and Mumford last week, he was considering the problem of classification of G bundles on a curve. So this means you have a curve X over a base field, okay? And for any parameter scheme, on this curve there was a whole scheme, G, and for any parameter scheme S over the base field, he considers the product S plus X. On this product, there is a group scheme, which is deduced from the group scheme on X just by playback, and then he considers the group of G principal bundles on S plus X. Of course, you can change the parameter spaces S, and so this means that you have a contravariant factor going from the category of schemes S over the field to group it. Okay, so this is the category called that pre-stack. In fact, I think it is in stack. And for completely general results, which were already considered by Ure, working under Grothendieck, and which were recalled in the lectures of Olivia, any such pre-stack or stack generates a topos, defines a topos, which is called by Giraud the classifying topos here for bundles, over the base topos, which is the arithmetic topos, the reticle topos of schemes. Okay, so there is this topos, you see, where we end up with a relative situation, the topos over the topos, and the base topos is the topos of schemes. So this means that on this topos, there is a natural structure shift. And just by playback, you get a structure shift of the classifying topos, and then you may begin to do geometry with all of. This was the starting point of the lecture course by Deligne and Mumford. Then, of course, it will happen that depending on the type of structures, your classifying topos may have some particular structure. In fact, it can be associated to a scheme, for instance, for some structures. I don't know, for instance, if you want to classify the curves of genus G with n parts on n is big enough, so it will just be a scheme. Otherwise, it will be a Deligne and Mumford stack. So this is that in some situations, you classifying topos as a structure which is closer to classical structures. So it may be a variety, it may be a Deligne and Mumford stack, or it may be more generally an algebraic stack. And of course, in these cases, you don't really need the language of toposes. But it may happen, and so this here is my conjecture about what Grothendieck meant. It may happen that for the very natural classification problems, you end up with a topos which cannot be a scheme, not even a Deligne and Mumford stack, not even an algebraic stack. So I can give you examples of that. So many of you actually know that in algebraic geometry, people especially look at the classifying spaces, the classifying schemes or stack, or abelian varieties together with a polarization. A polarization means that you are considering an abelian variety endowed with a line bundle which is angled. And in fact, this line bundle will allow you to embed your abelian variety in a projective space, and choosing once you have chosen coordinates, and so this means you end up with a problem of classifying subvarieties of a given projective space. And this was, of course, this problem was shown by Grothendieck to be always representable by a scheme. This is what he called inverse schemes. And then you have to forget the choice of coordinates you made. So this means you take the quotient by a projective group, and eventually you get like the right stack. Okay, so this is when you want to classify abelian varieties endowed with a polarization. But after all, you may decide, I would be interested in classifying algebraic abelian varieties without polarization. Okay? And for some reason, in fact, especially, for example, if you are interested in the automorphic program, in the Lambda program, this would be a natural object to consider. The classifying space of abelian varieties without polarization. Because you see, when you want to classify abelian varieties together with a polarization, you end up with symplectic groups. But if you forget the polarization, the natural group is GNR. And we are even more interested in linear groups than in symplectic groups. So it would be a natural object to consider. But because there is no more polarization, this classifying topos cannot be algebraic. It cannot be an algebraic stack. And a fortiori, it is not a Deligne and Mumford stack, it is not an algebraic stack. So here, the only structure we have a priori is the structure of a topos. And people did not consider at all this structure. But it would be very natural to consider it, but of course we will need to develop many tools to study that. For instance, just think about the following. We are used, especially when we consider moduli spaces, to look at their natural invariance. For instance, cohomology invariance. Okay? But cohomology invariants are defined for toposes in general. Okay? And then we may wonder, would we be able to say something about the cohomology of this classification topos, this classifying topos? So this is an example. In fact, in rencontrés, Grothendieck also says that, for instance, it would be a very important problem, a very important question to solve, to understand from the point of view of topos theory, what is the natural context for the six-operation formalism? Because this six-operation formalism was developed by him and later other people in some particular context, but he would want to understand this theory in general in the context of toposes. And if it was available, for instance, we would wonder whether this classifying topos of abelian varieties without polarization has a six-operation formalism or not. If it had, it will be consequences. I give another example, which is also very natural. In fact, in algebraic geometry, of topic with algebraic geometers, I sometimes, several times, heard people saying there is no classifying space for analytic shapes on a tube in characteristic P. Okay, so in algebraic geometry, there is a natural notion of analytic smooth sheet. Okay, and in fact, when you are in characteristic 0 with orthogonal techniques, it is interesting to look at the space of so-called local systems. And people say it does not exist in characteristic P. But you see, once again, you fix a cube, and what you can do is for any cube X over finite, and then you can consider an arbitrary parameters in S, and you can take the product X cross S. You have also sort of prime number n, which is different from the characteristic of the basis. And you can look at local systems, analytic local systems on X cross S. And this makes up appropriate. And of course, you have best change when you change S. So it defines a cross stack. In fact, even a stack, because it can be glued. And there is an associated classifying topos for that. Of course, it is not a schema, but it is when defined as a topos, it even has a structure sheet, just because it is a relative topos over a base, which is the topos of the parameter schemes S. So this topos does exist as a space. And so of course by now the question is raised, what can be said about this topos? But at least it does exist. And so I think it is a very important point of topos theory, which is the fact that it's substantially topos that when you look at toposes, everything you may want to study is well defined. General remark. But of course, so you have a well-defined object, but what is needed is to study it, to understand its properties. For instance, for this classifying topos of analytic sheets, would its cohomology be interesting? And here I have a bet, which is that this cohomology should be interesting because of the computation made by Grothendieck. Grothendieck has counted the number of analytic sheets parameterized by finite fields. And he has found the formula using the Loblanc correspondence for GL2. He has found the formula, and the formula has exactly the same shape as if this classifying topos was a slib. So, you see, immediately here you have a very deep question, and this question can be raised only with topos theory. So this is my tentative answer to your question, which I have also considered. So thanks for watching. Yes, and I may add that indeed the approach ratio and his construction of the classifying topos of a stack was very unlucky. So basically, it was not influential, I think, neither in the algebraic geometry community, nor in the categorical logicians community, to which I originally belonged. So in fact, that paper was quite despised. And Johnston in particular makes no mystery of taking that step. Yes, and this explains why they try to develop a relative topos theory in the interval sites instead of relative sites as we do for the geo. You see, so we are in some sense coming back to that geo. But we were very surprised with Ricardo, with my former
student to find out that that paper was almost forgotten. And instead for us, it has been the key for that, in this theory.
Just with the title of this paper is Classifying Topos.
Yes, the paper is entitled Classifying Topos. And it was really, not understood, widely not understood. Okay, so I think that it's time to introduce the next speaker. So let me just, so thanks again, thank you very appreciate.